Please welcome Philip Metzger, Research Physicist and Scientist Engineer of the Year for the NASA Kennedy Space Center.
Hi, thank you very much. I'm going to talk to you today about the energy barrier at the end of the world. Some processes in nature are continuous, like walking up a hill would be a continuous process. But if there were a series of ravines that cut across the hillside, then you'd have to stop and leap over those barriers every so often, and that would be a discontinuous process. Well, I want to make the claim that the growth of civilization is like a discontinuous process. Mostly it grows continuously, but there are certain barriers that we run into. We have had these barriers in the past. And when you get to one of these barriers, it takes the bravest of us, the most creative and the most innovative, to get civilization over that hump to the next level. The Russian astronomer Kardashev was looking at how do we find signals from outer space as evidence of alien civilizations. And he wisely noted that we shouldn't make the assumption that every civilization is at the same level that we are. Some civilizations could possibly be vastly older than us and far ahead. And so he came up with this classification scheme. He said a type 1 civilization is one that's sort of like us, basically like us. It's grown and spread across the planet, and it utilizes essentially all the resources of its planet. Whereas a type 2 would be a civilization that has gone beyond its home planet, and it's using vastly more energy, up to the energy of an entire star. A type 3 civilization would be one that has gone into interstellar space beyond a single star, and it's using the energy of an entire galaxy. And he noted that if there are any type 2 or type 3 civilizations out there, their signals might not look the same as our own. Well, what I want to say is, what about earlier categories? Let's think about where we've been already, and what does that tell us about the growth of civilization? We could continue the numbering scheme backwards. So maybe a type 0 would be a civilization that's encompassed an entire continent. It hasn't yet developed the technology or the social structures to span the oceans and to become a type 1 civilization. Spanning the oceans was quite a feat. It was only done about 500 years ago, and we often create the analogy to space flight. It's a good analogy. Going back even further, we could say a type -1 would be a civilization that encompasses an entire river valley. The birthplace of civilization were in 4 river valleys: the Nile, the Mesopotamian, the Indus River Valley, and the Yellow River. And when people figured out there was a vast quantity of energy that could be had in river valleys by using humans and animal labor to do irrigation, to grow crops in the rich soil from the floodplains, you could have such a concentration of food energy that you could support a larger population than we've ever had in one place before. And that was the birth of cities, of civilization. It was a big leap forward. But going back even further, let's say a type -2 would be isolated enclaves when humans were pre-agricultural, when they were doing hunting and gathering, they would find safe places to live. Now, if you think about it, going from one type to the next always involves a leap. First, you have to leap beyond the limited energy in one area and the safety of your enclave, set up social institutions to enable large-scale agriculture. Once they got the large-scale agriculture, the cities rapidly filled out the floodplains, but they didn't go beyond that because they didn't have the logistics or the transportation or the armies to protect the logistics to send large quantities of food outside the river networks to support cities in the mountains or across deserts, for example. Once they got global or continental size empires, then we could fill out the continents, but it was another leap to go to an entirely planetary global civilization. Well, we've reached another one of these points now. We are starting to feel the barrier, the next limit that we're pushing up against. We're already feeling it. I just want to point out that all of the global challenges we're facing are really symptoms of one problem. It's that we've reached toward the limit of a type 1 civilization, and we're hitting the barrier that we've got to leap across. So here's some predictions. We are essentially type 1 right now. I don't think we're going to get any closer to the technical definition of type 1 than we are today unless we can go beyond the planet. If we do go outside a single planet, I think that within 50 to 100 years we would reach type 2 already. Or if we don't go outside the planet, we might never achieve it ever, because achieving sustainability where we don't use non-renewable resources anymore, people have predicted the Earth might only support about 2 billion people, and we're already way beyond that. So if we can't replace the non-renewables, then going backwards is really painful. And I think the only ethical thing is to go forward beyond a single planet towards type 2. If we do achieve type 2, the technologies indicate that leaping onto type 3 is no problem at all. The reason I say we're running up onto a barrier, and I call it an energy barrier, is because energy is really the key to everything. If you've got abundant energy, you can recycle and you can use resources that are not as valuable. It's really not a problem if you've got all the energy you want. All the indications are that the non-renewable energies, even with fracking, can't possibly last another century. They say we've got enough natural gas from fracking to last 100 years. That doesn't account for the fact that China is industrializing. They're now the #1 energy user in the world. They still are only at 1/4 per capita of our energy usage. India is industrializing. The world's population is still growing. If the entire world spends energy at the level of the US, we can't just replace the non-renewables. We need to replace them 10 times over. Even if we can reduce our energy usage by a factor of 3, that means with fracking we've only got 30 years worth of energy if the world all achieves a standard of living that the West has. So the sense that we're starting to reach the limits of our planet it's being felt by everybody. Even when you go to donate clothes, you'll notice that it doesn't say goodwill, it says planet aid. You donate your socks to save the planet. And there's a growing feeling, a growing sense that we really are at a point where everything we do is planetary, it's global, because we've reached the limit of a type 1 civilization. But I want to say we really don't have a resource problem. What we have is an imagination problem. We live in a hugely rich part of the galaxy. We have 1 billion times more of everything in the solar system than what we have on Earth. I didn't just say 1 billion just because I made it up. We really have 1 billion times more accessible metal in the asteroid belt. 2 billion times more energy leaves the sun than what falls on the Earth. There's 1 billion times more water in the moons of Jupiter than in the Earth. So the order of magnitude is billions. So there's really no resource problem. We just need to know how to go beyond this next barrier towards type 2. People say, think globally, act locally. Well, I want to say thinking globally is the new way of thinking too small. That's the problem, not the solution. We got to think extra globally. And people also say, well, let's think outside the box. That's good, but we can improve on it because it's not really a box that's our problem. It's the limitations of the sphere that we live on. We need to think outside the sphere. And when you've expanded your civilization all around the two-dimensional surfaces of the globe and you've filled it out, there's no other dimension you can travel in except perpendicularly outward towards space. A lot of people think this is not really feasible because it's such a paradigm shift to imagine transporting resources across the vast distances of the solar system. Well, think what a paradigm shift it was for the people living in the Pacific when the European ships showed up. You know, the people in Tahiti and Hawaii, they could actually cross the ocean without any significant source of metals, which limited their technology capabilities because they didn't have the resources that were available on some of the continents. But it was a heroic task to cross an ocean. Well, think about this little device here, this clicker. The materials that went into this include metal and plastic. The metals came from Africa. The plastic came from petroleum from Arabia. The materials were processed in America. Chips were made in America. It was assembled in China, and it was shipped back here and sold in the U.S. There's at least 4 ocean crossings that went into this little device that probably cost $15. The people in Tahiti just a few hundred years ago would not have believed you if you said that those ships carrying resources were possible and economical. But here we're doing it. There's no reason we can't take the next leap to go to a type 2 civilization. We are a species that has a history of leaping over these barriers. We've done it so many times before. We can do the next one. So people have started to envision what it might be like to have industry in space. In the 60s through 90s, Gerard K. O'Neill led the charge talking about manufacturing outposts in space. In his scenario, you would need 10,000 people working and living in habitats like this before it became economical, which unfortunately was a little too expensive for Congress to fund, so we didn't do it. In the 1980s, the Ames Research Center hosted a a summer study for self-replicating lunar factories. And this was an advancement forward, and they showed that with just 100 tons of hardware on the moon, you could set up one self-replicating node, which would then grow and produce this gigantic industrial power in space. Well, it was an idea before its time. The technologies weren't ready yet. And even 100 tons is a lot to put on the moon. That's a very expensive thing to pay for. But there's been some game changers recently. First of all, robotics has been leaping forward. And just go to YouTube and search for learning robots and see some of the things that are going on with robots nowadays. Computing speed. You need computers to have robots that can build things in space. Moore's law has continued without any signs of stopping. We're getting to the point where you can have a really smart robot on a small platform now. Manufacturing technologies. This is a revolution that's going on right now with 3D printing. We have one of our collaborators here from the University of Southern California. Brock Cachaneves is the inventor of 3D printing of entire buildings. So these are some things that are made with 3D printing. Another game changer is the discovery of ice on the moon. Our coworker, Tony Muscatello, said now there's nothing that can't be made on the moon because now we know the ice has nitrogen compounds and carbon compounds. Carbon, nitrogen, and hydrogen are now fully abundant, and we have everything we need for a fully healthy industry on the moon or in Earth orbit. During Constellation, we've used the funding to develop these technologies and test them, and we've shown that they work. We can use space resources. We can mine in space and build things in space. And we've tested these things in reduced gravity flights. There's Van Townsend and Adam Dokos, some of our coworkers, testing a plant that moves soil in and out of chemical processors, lunar soil. So we've proposed a new approach. I also want to mention, this isn't a part of my charts, but the International Space University just completed their 2012 study, and they've come up with a concept called OASIS, which shows how you can economically, every step of the way is economical to mining water in space, to producing propellants, and to selling them to a low Earth orbit space tug business that will carry satellites the rest of the way to high Earth orbit or geo orbit. And it'll vastly reduce launch costs. They've shown the business cases there. You can make money doing this. And so there's now a business case for people right now to mine the moon and begin doing industry in space economically without Congress having to pay for it. So the key idea is taking the next step beyond OASIS, beyond what ISU looked at, is we want to put industry on the moon. So don't launch it, evolve it. When the colonists came to America from Europe, they didn't put entire cities on ships and launch the cities. They just brought the tools. They brought the first generation of tools. The colonists had to build the second generation of tools, which are typically more crude than the first generation, and then they started working back upward from there. So you use appropriate technology. It doesn't need to be high tech. It needs to be easy to make in space. And we don't have to pay for all the technology. It's being paid for by this humongous technology engine that we have in our economy. We need to find them and spin them in. And finally, let's not forget that technologies are advancing exponentially. So let's not underpredict what's possible. An idea, a concept of appropriate technology, look at housing in America in 1620 versus what the Europeans were living in 1620. We need to be prepared to build things on the moon with inferior materials, but make them so that they can work with those inferior materials. That's the way we need to be thinking. Appropriate technology, water pumps. People found that if you deliver a high-tech water pump to an underdeveloped area, they can't maintain it because they need to maintain it with local processes and local materials. So with these things in mind, we've laid out a strategy, one possible strategy of 6 generations of spiraling technology upward on the moon. And we've shown that for as little as 60 tons of hardware, or even getting it down to 12 tons of hardware, you can get self-sustaining industry eventually within 6 generations to where you don't need to launch anything anymore. And then all you need to launch are the people to go out and enjoy what you're making and utilize what you're making. And so this industry can grow exponentially by the end of 6 generations. You could have 100,000 robots on the moon and 100,000 tons of manufactured hardware. And this is detailed modeling where we've shown this is feasible using technologies that are not too advanced beyond what we can do right now. There does need to be a little technology advancement, but it's not unbelievable technology advancement. Another 20 years, Beyond this, you'll have 1 million times the industrial output of the entire United States. And by the way, the next step beyond the moon is the asteroid belt. That's where you really want industry to be. And then 10 years beyond that, you've got 1 billion times the industrial capability of the entire United States. What could you do with 1 billion times the industrial capacity? Well, the question is really, what can't you do with 1 billion times the industrial capacity? You could have a global relief effort. You could land manufactured goods, land resources. You can bring beam energy down. You don't have to launch the energy generators. You can terraform planets and people can migrate to space. You could have the Asimov-type foundation as a backup to civilization. You could have the space endowment, which would fund things that people do in space. There's also the negative side. If we don't do this, somebody is going to, and we need to do it right. In conclusion, we are near the limits of a Type 1 world, and there is a barrier at the end of Type 1, and we're starting to feel it, and it's going to hurt, and it's going to hurt worse if we don't jump over it. It's going to hurt even worse if we try to move back. And so we need to leap over that barrier, and it's going to take the creative innovators to do that, and we need you to leap over the energy barrier at the end of our Type 1 world. Thank you.